Hello and welcome to another episode of the Elements of Deep Sea Mining. My name is Eric Young. With me today is Steinar Ellefmo, a professor at the Norwegian University of Science and Technology. Steinar was one of the first researchers in Norway to seriously model and quantify the country's deep sea mineral potential. In this conversation, Steinar walks me through some deep sea mining foundations. How do these deposits form? What kind of data do we have? We also get into the Norwegian political process and some of the confusion around terminology. Stick around to the last half of the episode where Steinar gives his thoughts on why people in this space so often misunderstand one another.
You will communicate your values to me so that I can understand your values. You will understand mine, and we will achieve some common understanding, and we can then recommend something. And that's a long-term project. It's not really something you do over dinner. It's something you would do over many dinners in really understanding each other and the luggage everyone brings in. That takes time.
If you're trying to make sense of where this debate is heading and what it will take to move it forward responsibly, then please enjoy this conversation with Steinar Ellefmo. Okay,
yes.
Ready to go?
Good, sure.
Okay, so then Steinar, thanks for being here today. If we can start with your background, where you come from and how did you get to be a professor, and then how did you get to focus on deep sea mining?
Are we ready for that long story?
Yeah.
I'm not sure you are, but we'll see. Thank you for inviting me. It's a pleasure being here. I'm Steinar, yes, born in Sandefjord, south of Oslo, 120 kilometers south of Oslo. Born and raised there. I decided very early that I wanted to be an engineer. Then I asked a cousin of my dad, who is an engineer, where can I study engineering in Norway? And he said Trondheim. He had studied in the US, but he said Trondheim. And then I very early on decided that I wanted to go to Trondheim.
How early are we talking? How early? Are you 8 years old?
Yeah, probably 7, 8 years old or something. I wanted to go to Trondheim to study to become an engineer. And then I had a very nice, normal, I guess, childhood in Sandefjord, growing up in a family of parents and a brother, big brother. I guess I was a quite normal kid. But then after the military, I did the military service. I went to Trondheim to study then geology, or I kind of aimed at petroleum, the petroleum sector, to put it like that. But I relatively quickly, I realized that I didn't necessarily wanted to study petroleum and wanted more to study, let's say, general resource geology. So I went on doing that. And I also realized that I had, let's say a mathematical touch, or wanted to have a mathematical touch to what I did. So I didn't necessarily wanted to study petroleum, but I wanted to do something mathematical with geology. Although not petroleum, I actually ended up estimating resource potential of some oil and gas resources offshore or on the continental shelf in Norway.
So I explain that just very briefly. So when you're an oil company going offshore, you want to know how much oil is in a potential area before you start to drill. So then you hire a resource geologist to assess the sort of quantity of potential petroleum there.
Yeah, well, in my master thesis, because this was then my master thesis, I worked basically not necessarily to estimate how much oil and gas you have in one specific accumulation or a field, but more what we haven't found yet. So how much will we find if we go to explore? This is, let's say, more than 25 years ago, I did my master's on this, because I kind of took that knowledge of predicting what we haven't found yet and associated disciplines into then a PhD that worked more on, or focused more on mining, onshore mining. So I did my PhD, was basically the mine planner for Rana Gruver up north in close to Mo i Rana for 4 years, doing a PhD on geostatistics, analyzing spatial data to try to predict variability and the expected amount, in this case of hematite and magnetite, and then incorporating that uncertainty that I then quantified into, let's say, the whole value chain of iron ore mining. So exploiting that uncertainty and doing that as part of the mine planning process. I was interested in mathematics. I've never been, let's say, excellent in mathematics, but I have had a sense for it. So I kind of took that through my studies and also my PhD to kind of work quantitatively. And then I took this PhD, I took a postdoc, and I was also out in the industry, and then I came back again to the university, and all the time I've kind of worked with numbers, trying to quantify, trying to estimate quality variation. So what do we have in the ground, and how could that knowledge be exploited when we plan the operation? And then back in 2010, we started to get curious about what haven't we found yet on the ocean floor. So going back to my master thesis, where I estimated what we haven't found yet of oil and gas on the continental shelf of Norway, we started to ask similar questions about what we haven't found yet on the ocean floor. So that kicked off, let's say, a pre-project, a project where we got some industry funding to complete a project where we estimated what we haven't found yet. And although I have been quoted on 1,000 billion kind of NOx numbers, very high numbers, what we actually, and that's true, we published those high numbers. What we also published was that it could be almost nothing. It was a big uncertainty. The uncertainty was massive. So through that study, we managed to estimate, let's say, an expectation, but also what it could be and what it could, or what the maximum could be and what the minimum could be. So we quantified that range, and it went from almost nothing to a lot. And it's a very interesting, let's say, exercise, because the deposits that we now have found, or not we necessarily, but University of Bergen, as you know, have done a lot of cruises. They have identified a lot of deposits or sites of interests. They are not necessarily a deposit, because that's a specific meaning in a mining engineer's head, to put it like that. So it's a site of interest, and University of Bergen and others have identified a lot of interesting sites. We also have been on a cruise back in 2016, the Marmine cruise. So we have been down there sampling, but then for a different purpose compared to what the University of Bergen has been investigating.
Sorry, when did you release the numbers?
Yes,
range?
exactly. Well, yeah. So those came in 2014. Those numbers with let's say a very huge uncertainty. Yes, because the deposits that we have on the ocean floor that have been identified, we have them onshore as well. There's not necessarily the very same deposit, but similar deposits made in the similar conditions, geologically speaking, that we have along the mid-Atlantic ridge today. So the deposits on Røros, on Løkken, etc., they are not developed in the exact same conditions, but let's say, geologically speaking, similar conditions. So we have them onshore, and from that perspective, we knew that they must be offshore.
Oh, very interesting.
So then we kind of start to be curious, actually, and started to ask questions. How could we potentially quantify the amount that we haven't found yet? And then, of course, we used knowledge from onshore, and we used onshore analogs. For example, on the island of Cyprus, the Troodos field, the geological conditions that we have there, geologists assumes that they are very similar, actually, to what we have on the mid-Atlantic ridge today. So we can use that as an analog. We have found, or our society have found, sites of interest along the mid-Atlantic ridge. So we had some data to go on. And we then kind of accumulated the knowledge, came up with this very, very uncertain number on what it may be out there. And after we published these data in 2014, new discoveries have been made. So I wouldn't say that our activity really, let's say, kicked off the whole thing, but I think we contributed. We had a small role in bringing attention to that there may be a potential there, or that there is a potential. But that potential is unreleased, to put it like that. So that's why we kind of kicked off, shortly after having published the results, we kicked off this deep sea mining pilot program, this interdisciplinary work that we did at NTNU, trying to look different aspects of deep sea mining. So I guess that's kind of my way, in very, very short or few words, how I'm a professor in 3D modeling, basically, spatial geological modeling. And I have then experience both from onshore mining. I have done related stuff then during my master thesis for the oil and gas. And now I've done those kind of activities also for deep sea mining.
Okay, so this is great. So this was one of my questions, was kind of when did the deep sea mining conversation get going in Norway? And so when you released this report in 2014, there wasn't much public or political attention to the potential of minerals in the Norwegian kind of ocean zone.
No, but that said, as I said, we kicked off this work on we kicked off being curious back in 2010, 11. I can't really remember exactly. But so in 2012, if I remember correctly, and in 2013, we organized in cooperation with NGU, the Geological Survey, we organized 2 workshops on deep sea mining. So we had international experts presenting so from Germany, also Russia, the US, if I remember correctly, international experts presenting kind of their work, and then the discussion, let's say, gradually kind of kicked off. And I guess it got some attention when we published our results back in 2014, but it didn't really kick off then either. I claim that we have a small role in it, perhaps, in the attention, but of course, the real attention, growing attention, came with the bigger geopolitical aspects of things and increase in commodity prices and the green transition and all those.
Once the IEA started releasing reports on how many minerals were going to be short in meeting the energy transition goals.
Yeah.
Okay, so then I'm hoping we can kind of give people a real foundational understanding of marine minerals. So can you, start, I guess, with describing the different types of marine mineral deposits, where they occur, and also we'll get into how they come to be there.
I would say that, there are different ways of categorizing this probably, but I would say it's 3 to 4 major types. 4 because lately this fourth type have emerged as something interesting. But what we have worked primarily with is the so-called seafloor massive sulfide deposits. Those are the kind of deposits we have onshore Norway, in Røros, in Løkken. And they are formed through hot fluids penetrating down into the ocean floor. The water is then heated up, can be 300, 400 degrees water. It's kept fluid due to the high pressure. These are very deep, so 3,000, 4,000, 2,000 meters water depth. And the water is, of course, in the ocean floor. So they are kept fluid due to the high pressure. They dissolve the metals that are in the ocean floor. And then if all this water is kind of focused along some fractures or faults or something that can facilitate this hydrothermal flow, those fluids may come out at one single spot. And it's almost impossible to predict where that will be, but the water will kind of find its way up. And we say that we have then mineral-laden fluids, so fluids with minerals, with metals in them. And then they meet this very cold water. The ocean can have minus degrees water temperatures, on or close to the ocean floor. So these very hot fluids meet that very cold fluid. You can imagine then that the minerals that are in these hot fluids kind of drizzle out. Yeah, they kind of are precipitated from those fluids, and they kind of accumulate on the ocean floor or in the ocean floor. So it's almost like a trap, that the ocean works as a trap that then traps the minerals containing the metals, and then they are accumulated there.
Does this also happen, like this precipitation happens underneath the ocean floor as the hot water comes towards the surface? It cools in whatever fissure it's in, and some minerals precipitate out before it reaches the kind of open ocean? or it happens once it's out in the ocean?
No, it can precipitate also before it reaches the ocean floor. There are, how should I put it? There are conditions that makes this precipitate. It can be temperature, it can be pressure, it can be that it meets some rock which is chemically different that makes the water precipitate whatever it contains, or at least some of it. So you will often see that, well, in the southern part of what we call the Moon's Ridge, which is a part of the Mid-Atlantic Ridge within the Norwegian zone, on the southern part of that Moon's Ridge, we have some sites of interest, the Troll Wall, discovered by University of Bergen, for example, which and the water depth is relatively shallow there, 800 meters or something like that. So that site of interest would potentially, I haven't really seen samples, so I should be a bit careful, but I would expect that to be higher, for example, on zinc and very low on copper. Because then the copper has been deposited or precipitated further down in the crust, in the ocean floor. So if you were to dig, I wouldn't recommend it, but if you were to dig, let's say 1,000 meters down in the ocean floor, beneath the Troll Wall, you would probably, I shouldn't say probably, but you may find the copper, because the copper has then precipitated at other conditions than the zinc closer to the surface.
Because there's something about copper that makes it precipitate out earlier in the process.
Yes, exactly.
You've mentioned Røros a couple times, and so for people not familiar with Norwegian tourism as well as geology, can you tell the listener about Røros and the history of that mine? Because I think it's a little bit interesting also. You've said that this type of offshore mineral formation is the same that happens onshore Norway. So tell us a little bit about the history of Røros, and also does it happen in other places, or is this something that's specific to offshore and onshore Scandinavia?
Well, if I may, we shouldn't say that it's happening in Røros now, because the formation of these deposits are not happening in Røros now, or it has never happened there. It has happened on the ocean floor.
Yeah.
So Røros used to be on the ocean floor at great depths. But then during, let's say, the geological history, it was brought onshore. And that's a long story, and I'm probably not the best one to actually tell that story. But whatever has been formed on the ocean floor has now been brought up onshore, so that we can actually investigate it, and it then were mined from the 60s till 1970 something, 8, I think. I shouldn't be too specific on that. But the 1970s, and it was mined primarily then for copper, but they also opened up more zinc mines. That again goes back to the formation and the precipitation of the different metals, because these different metals would precipitate in different sections of the crust. And once they have been brought up to Røros, where they are today, you will find these as, let's say, separate deposits, separated physically, that you have a zinc mine and a copper mine. That said, both the zinc mine and the copper mine would probably contain both metals, but to a greater extent, it will contain copper, and to a greater extent, zinc. So again, this geological history of the metals being separated, you will recognize then when you go to Røros that some of the mines are more zinc-rich, some of them are more copper-rich.
Right, and I just wanted to stress that Røros is just kind of, it's a traditional, what people think of as an underground mine. This is the way that ores form. It's nothing specific. There's nothing unique about Røros. And it happens to have been mined since the 1600s with underground mining dating back. And there's a very interesting mining museum that people should go and visit and see how they've been mining since well before the invention of dynamite.
Yeah.
So this is the SMS type deposits.
Yeah, exactly. Thank you. So that's the SMS type deposit. And then we have the nodules that are in particular known from the Pacific, from the abyssal plains, the very deep ocean floor in the Pacific. They are fist-sized potatoes lying around in particular areas where you have very, very slow sedimentation rates. Because these potatoes, if you can call them that, precipitate directly out of the water. So you will have to have a seed. It can be a piece of rock or some shark tooth or something that the metals then starts to form or precipitate onto that seed, and then you kind of build concentric layers of then metal-containing minerals. And you have enormous fields of these nodules, in particular in the central part of Pacific, in the Clarion-Clipperton fracture zone. Massive field of these nodules. So they are lying around there, and they contain typically some nickel, copper, rare earths, manganese. They can contain some cobalt, all of which are very relevant for this green transition and our transition, hopefully, towards an increased, let's say, portion of renewable energy production. Very similar are the crusts, the manganese-rich, cobalt-manganese-rich crusts that are really precipitated very similar to the nodules, but they precipitate on sea mounts or mountains on the ocean floor. So they need a substrate, some sort of a piece of rock or a big piece of rock, a mountain, that started then, if the sedimentation rates are low, the metal starts to precipitate out of the water. So, and that's metal that is in the water. And to some extent, it's back to the SMS that kind of dissolve metals from the ocean crust and then spits out these hot fluids. That is metal containing. So that is kind of dissolved in the water and then could be precipitated again as crust or as a nodule. So we said that the nodules can be perhaps a fist size. The crust can typically today be up to 20-25 centimeters thick. So they are thin, let's say, crusts, hence the name, that are covering, let's say, often very steep slopes on these sea mounts or these mountains. So if it's not steep enough, you will have sediments that accumulate, and you will not get these layers of these metal-containing minerals precipitating on the seamount. In order to make these crusts, you need to have, and the nodules, you need to have very, very low sedimentation rate. And in case of the crust, you can typically have currents that kind of remove sediments, or you may also have as I said, very steep slopes, so that sediments will just fall down, basically. And then the fourth one, it hasn't been up in the media that much, but that's rare earth element rich muds that has been found in the Pacific, where you have thick layers of mud, and part of those in some instances contains a significant amounts of, in particular, rare earth elements. So these 17 very specific metals that we rely on in battery technology, in the green technologies, basically. Those are basically and again, those are also, as far as I know, exactly, or at least also precipitated then from the water, but are also very often associated to shell sand and shell fragments, bones, etc. In some instances, you have this accumulation of those bone fragments or shells, and those can be then rich on these rare earth elements.
Great. So for people like me who never really thought much about why we have mineral deposits, minerals are actually just deposited everywhere, but in a very diffuse way. They're in seawater and they're just in rocks, in the earth, everywhere. So to find a deposit where they're in a significant concentration to make it worth trying to extract and process, there has to be some sort of circumstance or process that takes what is generalized and diffuse and concentrates it in some place. And so with the seafloor massive sulfides the circumstance is essentially these geysers of hot water that is coming up from the subsea rocks, and the interface with the temperature change and I guess a pressure change that can make the minerals precipitate out. And with nodules in the crust, then it's something that's going to happen just from the seawater. And then there the key is absence of sedimentation that's going to bury these things faster than that process can happen. You said that the Clarion-Clipperton zone, you called it the Clarion-Clipperton fracture zone. So is there also an underground geological process that makes it more likely that, like, are there more minerals there, or is it just that it's so far away from any onshore rivers kind of releasing sediment into the ocean that it's so far away from sediment that's the reason that it happens there?
I mean, that's a good question, and I'm not sure I can actually answer it perfectly here. It is far from everything, so the sedimentation rate is very low. There is a fracture zone. There's an actual fracture zone. If you go to Google Maps, you can actually see the fracture zones. So this zone is kind of bounded by large structures. Whether that gives some particular oceanographic conditions that makes this precipitate more there, I don't know, to be honest. So, but of course there are very low sedimentation rate out in this region. So I guess I would say that's the prime cause of us having an high accumulation or coverage of nodules in this area.
And then deep sea mining. So first of all, is there a specific definition of deep sea? And then is there a reason why this kind of why these economic mineral deposits tend to happen in the deep sea, or do they also happen in the shallow sea?
No, they don't happen in the shallow sea. Then you would have to go into the ocean floor. With deep, you normally say deeper than 200 meters. Yes, sorry, 200 meters. For the SMS, you will not have a deposit or a site of interest, an accumulation of something, unless it's deeper than 800 meters. So on the ocean floor, you will not have any accumulation of metals, to put it like that, if it's shallower than 800 meters. That's the rule of thumb.
And that's because this is where the seafloor spreading happens. It happens in the very deep sea? No?
No. I mean, it happens on Iceland. That spreading is happening today onshore Iceland. So it doesn't have anything to do with that. But it's basically that if you are shallower than 800 meters, the precipitation of these metals have already taken place in the crust, in the ocean floor, when it comes up to the ocean floor. So then the precipitation have already taken place deeper than 800 meters. So that's why you don't. So if you were to mine, God forbid, but if you were to mine these deposits shallower than 800 meters, you would have to go into the ocean floor, really dig down and into the ocean floor. And doing that, I wouldn't even think about it.
That's a combination of deep sea and traditional underground mining.
Yeah,
that sounds like a nightmare.
Exactly.
Yeah, okay. And then you touched on it, but so how do these minerals compare to land-based resources? Is the mineralogy different in some way, or is it just kind of similar combinations of minerals and similar grades, but just 4 kilometers deep?
The minerals are basically the same. Of course, I would say that all deposits are unique.
Okay.
So, and that goes from those on the ocean floor, but also those onshore. Every deposit is unique. So they don't necessarily contain exactly the same minerals, but generally speaking, both deposits on and offshore contains the same minerals. The minerals are components that contain the metals. So the metals are in the minerals. And on the ocean floor, you typically see that you have more of the mineral containing the metal than you have comparably onshore. So the metal grade, the percentage of copper, the percentage of zinc, for example, will typically be higher on the ocean floor.
Is that just because we've mined the higher grades on land?
That's a good question. No, we haven't really seen those grades that we at least have seen on the ocean floor. I mean, very few of these deposits have actually been drilled. So we don't really know the interior of the deposits on the ocean floor. I guess it's the Solvara 1 deposit in the Bismarck Sea off the coast of Papua New Guinea, who is the one that have been explored the most by Nautilus Minerals. They have really drilled it, and the grades that they found there is significantly higher than what we have found onshore anywhere. The reason, of course, the deposits that, generally speaking now, the deposits that have been found onshore, they have, of course, been through million years of influence from a great variety of geological processes. So they have been altered. They have been changed. There may be secondary influence from fluids that have then leached some of the metals. So a deposit is a very outcome of a series of unlikely events, all of which are unlikely. And one of those unlikely, let's say, events is that the grades are preserved, that they don't leach out, that the metal don't leach out after it has been precipitated. So, and the likelihood of leaching something out increases with age. So the deposits that have been formed on the ocean floor that is now on the shore, they have probably undergone geological processes that may have leached out some of the metals. So the deposits on the ocean floor, they are fresher and they are therefore higher grade, simply put. And but then grade, so grade is the percentage of whatever you are interested in. And this is not only what makes a deposit valuable or not. We talk about textural differences, so textures that can be grain size, how big are these mineral grains, what are the grain shapes, what minerals are kind of bound together, how are they paired, and if you start to crush this to actually extract the metal, how easy it is to break the minerals from each other so that you can actually say, I would like to have that mineral, but I would not like to extract anything from that mineral. So those properties and characteristics are very, very important as well when it comes to whether a deposit is profitable or not. And as we have seen, it seems like, at least from the samples that we collected in the Marmine project, it seems like these deposits are finer grained, which doesn't necessarily have to be an advantage. Whether that is reality if we had drilled into the interior of the deposit, that's another question. I would think that it would have turned coarser grained, which again would make it easier to process. But this is something a mining engineer would have to study. What are the grain shapes? What are the grain sizes? What are the grades? Yes, the percentage of copper is important, but this is a material that you are going to mine, and then you are going to put it through kind of a factory that separates the valuable from the not valuable. And how easy that is really dependent on the mineralogy, what minerals are there, what the grain sizes are, what the grain shapes, intergrowths, etc. So there's a lot of, and all of these things can and will be different from one deposit to the other.
Okay, so you've said a couple of times that if we had drilled farther, or if we had drilled more to define what's down there. So can you give the listener a little bit of an idea of the process of defining and getting more information of these deposits?
Well, it depends on what deposit type you are talking about. I worked primarily with SMS, the seafloor massive sulfide deposits that are formed through this hydrothermal circulation. And those are, when water comes up to the ocean floor, you get these black smokers, these pipes, and they will, under their own weight, they will collapse. They can reach, let's say, 10, 13 meters, 50 meters, and they will typically collapse. But the fluids will still, so then that will build up a new black smoker that will collapse, and a new black smokers come up. So you will kind of build up almost like a small mountain of gravel, basically, sand and small rocks that are, call it a remnant from these black smokers, which could be mineralized. It could be metals in them. So they collapse, built up these small mountains. They could be, let's say, 50, 100 meters tall. They could have a diameter of perhaps 100 meters. So you have these dome-shaped structures, and beneath them, you will also have a stringer zone, a feeder zone, where these fluids have kind of followed cracks in the ocean floor, and you will have precipitation of metals in that feeder zone as well. So you have these cone-shaped things below, and you have these this dome-shaped, or not a dome, a small mountain on the top. And in order to assess whether that can be mined, you need to know the geometry of the cone, of that surface expression, which you can get from bathymetric data. That's ocean floor topography. You can collect that through a variety of technologies, and you can get some impression of the size of that structure that you have on top of the ocean floor. And then a really rule of thumb says that the diameter of that small mountain equals the depth of the cone.
Okay.
Of course, that's a really rule of thumb, but since we haven't really drilled many, we need to develop such rules of thumb, and they are really rules of thumb. But they kind of indicate to us how deep these feeder zones may be by just looking at the surface expression of that small mountain. Yeah, and you can use geophysics, for example, to get some impression of the geometry. There are geophysical methods that measure the conductivity of the ocean floor. So how easy is electric power kind of transported in the ground?
So you stick two electrodes 100 meters apart and try to send some electricity from one to the other?
Yeah, something like that. Often you set up a magnetic field. That magnetic field will induce electric currents in the ground. That electric current, again, will set up additional magnetic fields, and then you can measure that additional magnetic field. And by measuring that, you can calculate how conductive the ground can be. So by then collecting that kind of, and there are other techniques, that kind of geophysical data, you can get an impression of the geometry of the deposit, the stringer zone, the feeder zone, and that structure on the surface. But in order to really know whether you can drill it, you need to know the particle size, as I talked about. You need to know the grade, particle geometry, or the shape of the particle, of the mineral grains, etc. And in order to do that, you need to drill. Often you would drill so-called core drilling, where you drill basically drill a pipe into the rock, and then you get a, how should I put that, kind of a cylinder of rock, where you can actually then investigate it. As a geologist, you would investigate it and you will assay it. So we will measure the amount of copper, or the portion of copper, zinc, etc. And you would investigate it with a great variety of techniques to exactly learn about the textures of these deposits. And then one hole is really not enough. You would have to have many holes to actually know, or at least think you know, the actual characteristics of that specific deposit. And how many holes you need? I think that's a topic on the Deep Sea Mining Conference that will take place in Bergen, beginning of April. I think they actually have a panel debate on how should we think when we decide how many holes we need to actually say we know the characteristics of this deposits.
That's interesting, because this is, I mean, what you're describing is standard practice for above ground assessment. So
Yeah.
they can't just take the same mathematical model and apply it to the deep sea.
Well, there are no mathematical model that is applicable onshore for all deposits. That's always a assessment done by a competent person. And a competent person in this setting is a person that has sufficient experience, education from the specific deposit type that is being studied. So in order to be a competent person, you have to have at least 5 years of experience in characterizing and describing and estimating the copper grade, for example, of that particular deposit type. And then it's up to that person to assess that for this deposit, I need to have a drill hole for every 20 meters, for example. But that's up to that person to actually assess, discuss, document that if I have that, I am certain enough to say that this is a good or well-described, well-characterized deposit. That kind of experience we don't have from the sea. So you will have to kind of use your experience, learn from onshore mining and apply it offshore. But we cannot really just take a mathematical model and apply it. And I think that drilling onshore is one thing. That's expensive of its own. Drilling offshore, I mean, the logistics when you drill offshore is much easier because you can just go by the vessel and then you are on top of the deposit. Mm-hmm. Drilling offshore, onshore is a logistical nightmare, or at least it can be. To bring the drilling rig, you may have to fly it in with a helicopter, etc. So the logistics is much easier. But actually drilling an SMS-type deposit is really challenging. And if you dive into the drill hole data collected by Nodules minerals, you will see that the core loss is significant. A core loss, I talked about that you bring up this cylinder of rock. If you have core loss, you have lost a part of that cylinder. So that has gone away somewhere. It may have been just some clay that just, when you took it up, it just vanished into the water column. Mm. And you have a high degree of core loss because the rock itself is rather fragile. And so when you drill, you will not necessarily get up the whole core.
Sorry, and this Nautilus minerals, that was the development in Papua New Guinea.
Yes.
And that's, I guess, I don't think you said that explicitly, but that's the same kind of mineral deposits that we have in Norway. So that experience, I think because it's in the Pacific where there's the nodule mining, I think a lot of people naturally assume that that was a nodule mining operation.
No, that was a seafloor massive sulfide deposit or deposits that they developed. And that's the same, let's say, similar deposit type that we have inside the Norwegian jurisdiction. I should point out that there are 2 of the 4 deposits types that we have inside Norwegian jurisdiction. It's the seafloor massive sulfide and the crust. Mm-hmm. So we have both of them. As I said, I worked primarily on the seafloor massive sulfide deposits.
And so you're using data from Papua New Guinea because that was somewhere where there was a kind of a higher amount of drilling that happened to really explore the deposits. And that hasn't happened yet in the Norwegian context. Nope. What has happened so far? Like how much drilling has been done? Is it that they've taken a couple of samples in a couple of the mounds?
The Petroleum Directorate, now the Offshore Directorate, the SODIR, they did drilling activities. When was that? 2 years ago? Time flies. So they drilled, tested some new technology. They collected material, but as far as I know, they didn't really, let's say, manage to drill the amount you would have to. By far, I would say, you would have to in order to really delineate and appraise, explore, characterize a deposit. So they tested a hole. To be honest, I'm not sure. I was not part of it, so I don't really know how deep they drilled. I don't think they managed to drill that deep. I think the total amount of core was not really big. But for sure, they got some very, very interesting samples. But I also think that they realized, or we have realized that, and we knew it, drilling in these conditions are not necessarily a walk in the park, to put it like that. The logistics on the surface compared to onshore, easy peasy. That's a walk in the park. Of course, it can be tough conditions if you go up during the winter time, but during the summertime, you can often have very good conditions so that the operation on the surface is quite easy. But drilling and collecting enough samples to really we call it classify the resource, as we have three categories: inferred, indicated, and measured. In order to really say that we have something that can be mined, we have to be able to classify it as either indicated or measured. If a competent person says we only have inferred resource, you are not, according to international, let's say, rules, you are not allowed to call it what we call a reserve. So resource in the ground, reserve is what we will get out if we mine. So if you only have an inferred resource, you are not, according to these rules, you are not allowed to calculate a reserve. Or that said, you can always do a calculation like any other engineer would do. He or she can calculate something, but you're not allowed to call it a reserve, because a reserve has a specific meaning, and you have to be very careful of using that word. So on the continental shelf of Norway today, we don't have any reserves. I would say we don't have any inferred resources either. Inferred perhaps to some extent, but really no. I wouldn't be able, I don't have enough, let's say, experience to actually call me a competent person in this setting. So from one who is not a competent person in this setting, I would say that, and I would say no one are. We don't have competent person. We have naturally a lot of competency out there. There are a lot of competent persons, but they are not necessarily competent in this setting. I would say that we don't have even inferred resource. We could say we have exploration results, but we cannot classify them as an inferred resource. And in our 2014 estimate, we talked about speculative and hypothetical resources, which is according to a US Geological Survey classification scheme. You are allowed to call something resource if you put speculative or hypothetical in front of it, indicating that you haven't really drilled that much, but you are, as a geologist, you are kind of speculating, or you are putting up hypothesis about what it may be and what we may find if we explore.
Okay, so then, so I guess this is a good segue towards where we are in the Norwegian process. So, about a year ago, I guess in early 2024, there was a lot of international headlines about Norway having opened for deep sea mining. So can you give some background on that process, what was actually decided, and where we are now?
I think that is, if you ask me, I think that's one of the bigger misunderstandings in the whole process here. Norway, or the SODIR, they confirmed a regional environmental impact assessment, which has been criticized a lot. Yeah. Based on that, they opened up for, let's say, mineral or mining activity. They never, ever have said that they have opened up for mining. And so mining and this mining activity that they have opened up for, in my head, is on different planets.
Right.
The mining that they are talking about would be totally destructive, but then you would actually destroy, probably, depending on technology, you would influence at least the habitat, for sure. What they have been talking about now is to open up for mining activity, whatever that means, to collect data, to capture data. And people may disagree with me, but that's what they have suggested to open up for. Collection of data so that we can make even better informed decisions on whether we should open up for mining. And that's downstream. That decision is not what we have been discussing or that has been decided. Of course, if you kind of say no to more data, you will never be able to open up for mining. So, of course, it may be an effective way to actually stop mining is to say no to more data, no to more knowledge. So in my head, I think it's probably not, I would argue it's not necessarily a wise idea to stop collecting data. I think we should know more, and that's basically what the opposition towards the whole process also say. We don't know enough, and I totally agree. We don't know enough about the geology. We don't know enough about the ecosystems. We don't know enough about the technologies. So how can we even talk about impacts if we don't know how we are going to do it? If you ask around, there are concepts out there, there are drawings, there are ideas on how we can mine this, but we haven't seen the technology that will actually mine these deposits. I'm quite sure we can say that there will be stressors, there will be impacts or some sort of impacts or stressors, but as long as we don't know the ecosystems, we don't know the technology, we don't know the geology, how can we even talk about an impact? I used the word impact, but I meant stressors. So we will probably stress it to some extent, but we don't really know how much yet because we haven't developed the technology. So I think we are now in the stage now is that we have postponed the announcement of areas that can be applied for a exploitation permit.
Exploration permit?
Well, you can apply for both, okay. Exploration and exploitation. And if you translate exploitation, it's about mining, perhaps, or that's, I guess, the common understanding of this license in Norwegian, exploitation license. And with utvinning, we understand mining. Right. Which I can understand. And I think that was the wrong word to use about this, because it is misleading. Because if you apply for an exploration license, the business model then would typically be to collect data and sell it. Because if you get that exploration license and you find something, you don't have any priority in actually being allowed to mine it. Okay. If you apply for an exploitation license, that would typically be someone who aims to be an operator, because then you would have to explore, collect data, analyze data, do an environmental impact assessment, understanding the impacts, because then you have decided on the technology, so you can start to talk about impacts, understanding them, and then you have to apply for a concession and the right to actually mine. But that's a massive, long process where you have to really collect data, tons of data, in order to actually document that you can do this in a responsible way, or I'm not sure we should use sustainable way, but at least in a responsible way.
Okay, so why did they need to open for licenses if, so as you say, the Norwegian Offshore Directorate, the SODIR, has gathered some data. The University of Bergen and others has been out exploring. And then there was this process to open certain areas for some vague licenses, whether they were exploration or exploitation, was certainly a semantic stumbling block that I think, I imagine everyone is regretting.
I hope.
But yeah, first of all, why can't we just ask the SODIR and the universities to go and get more of this information? Why do we need to get concessions in order to bring in this data?
Well, remember that we will not need concessions to bring in new data. You would have to bring in new data as soon as or before you apply for the concession. And I think that for sure, SODIR and the university should get the opportunity to collect more data. I think, that's my personal viewpoint, I think that we will be much more effective if we allow companies to also collect data. Of course, then you have to have some arrangements which may be naive, I'm not sure, where we can actually exchange data. But Norway has been quite good at exchanging data. So I imagine, and I would hope for that we could open up for a partnership, public-private partnership in collecting data, making sure that we can share data to make good decisions on whether we can do this responsibly or not.
And so in order to motivate companies to invest money in data gathering, which in this environment is extremely expensive, you need to offer them some carrot. And in this case, the carrot was, we'll give you kind of proprietary ownership in the future over mining that happens in a certain area if you go out and explore in that area. So kind of in exchange for you spending private resources on gathering data here, we'll give you first kick at the can of exploiting that if we get there.
Yes, that's right. I didn't mention that, but if you apply for and get this exploitation license, you have the first priority to actually get access to mine whatever you find if you can document that mining can be done responsibly. So that's the carrot. I kind of think that, and that boils down to the dilemma that our society needs minerals. And I think we need to investigate whether deep sea mining can play a role. That's, in my head, that's what we are in the process of, investigating whether this can contribute. And then, of course, there are a number of other sources and a number of other, let's say, actions we need to take to meet the future demand of minerals and metals. And deep sea mining may be one of them.
Okay, so if I was a benevolent, private actor, can I go out and start collecting this data now? If I say, okay, I'm not so interested in having first dibs on exploiting, but can I organize a ship and take it out there and start helping to fill in this data, or that's not allowed yet?
Only universities and the soldier itself can go out to explore.
From my perspective, there's been, there's been misunderstanding about what has actually been opened for. And then there's also been, I think, a trust issue over when people, once they understand that, no, we're going to give these companies kind of preferential licenses to mine an area, but we're not giving them licenses. There's going to be a whole application process involving an environmental impact assessment, and that has to go back to Parliament in order to be voted on. I think people who do understand that, but still advocate for stopping the process right now, feel that it's a slippery slope, that handbrake that is in the system is never going to actually be pulled once we get companies to invest in this. Then there's going to be reluctance to actually stop them before mining. I don't need you to speculate on that, but I would like to hear your thoughts on kind of the timeframes that we're talking about. So as you say, we have very little data. We have to start by not only environmental data gathering, but also even kind of mineral data gathering to find out if this is economic. So in your mind, if things happen at a reasonable pace, like how far away would a company be from being able to say, okay, we're ready to mine in the Norwegian area?
Well, one thing, yes, many are claiming we have little data. Just to comment on what you said, some argues that we have a lot of data. But again, we don't necessarily have enough data to assess the consequences or the impacts from one specific mining operation. So we have a lot of data. University of Bergen that we have mentioned have done a lot of investigations on the mid-Atlantic ridge. There are global data. The Germans, the BGR, has done globally a lot of investigations. Private companies have already done a lot as well. So there is a lot of data out there, but we don't necessarily have enough data to actually assess the impacts from a specific mining operation. And in order to come there, I mean, one thing is for a company, it would have to actually, as we talked about earlier, drill and collect and analyze geological information. And you would have to collect a lot of information about the ecosystem, oceanographic conditions. That needs to be analyzed. So for a mining company, I mean, I wouldn't necessarily want to put myself in the shoes of a private company here. But looking at how the time frame of getting a mine up and running onshore in Norway, which could take 10, 15 years, 20 even. I'm not sure we are quicker offshore. But it's difficult to predict about the future. I mean, looking at the process onshore Norway, I'm not sure, of course, the spatial, let's say, area conflicts that we have offshore may not be as significant as onshore. So you can't really compare them 100%. But still, looking at that process, which may take everything from 5 to 20 years to get from exploitation license to an approved mine plan, and then you have the concession and you can start, takes up to 20 years. So it may be that industry have to have that perspective. And then we have to spend those years wisely and collect as much information as possible through, I would say, private-public cooperation. You have to make sure that we can share data. You have to start trusting each other. And we have to earn the trust, all of us, in order to, as I said, make good decisions. Because, again, it boils down to the dilemma. We need we need minerals. We don't necessarily need minerals from the deep sea. That's not what I'm saying. I'm saying that we need minerals and metals. And whether they come from the deep sea, yes, perhaps. They can come from onshore. Recycling, we have to start spending less, etc. There are a lot of actions that we should to, as I said, meet the demand.
So I like that you kind of mentioned that we need to earn trust. And you've been involved to some degree in the public discussion around deep sea mining in Norway over the past few years. And I guess you've experienced that the discussion has really heated up in the past few years. So I wonder if you want to just kind of say a little bit about what it's like, how you experience the public debate, if you think that the amount of attention and controversy has upsides as well as downsides, and what needs to be done in order to make the public conversation constructive.
I think it's really, really difficult. I think at least the conversation or dialogue or discussions that I've been part of has to a great extent, and it kind of took me a little bit too long to really understand that, for example, a lot of the opposition thought that we knew everything about the geology. We don't, and we didn't. So I guess this points to the fact that we don't necessarily understand each other. We are scientists, we are representatives from the industry, we come from different backgrounds, we have completely different perspectives on things. Just a simple concept like uncertainty. What does that mean to you, and what does it mean to me? And that process of us understanding each other, or at least trying to understand each other, has, I think, been challenging. And I'm not sure we are there yet, that we fully understand each other. And I think that's one of the big hurdles that we have to jump over, to put it like that, before we can actually have a very constructive dialogue towards finding good solutions. So we have worked a lot since 20. We have worked, as I said, as I mentioned, this deep sea mining pilot program, which is not necessarily a pilot in actually going out mining, but it's more a pilot in interdisciplinary research towards making a decision about yes or no to deep sea mining. So we have had PhDs and postdocs working on also, not all, but geological aspects of deep sea mining, technological aspects of deep sea mining, philosophical, ethical, historical aspects of deep sea mining, biological, ecosystem types, environmental aspects of deep sea mining. So, and in that process has been very interesting and frustrating to some extent, because you really realize, and I think we are there still, realize that people don't understand each other. And that's a very negative and pessimistic, let's say, standpoint. But I think, in fact, it's true. And we need to actually realize that and start to ask questions. And if you, as a scientist or someone in this debate, get questions that you find is funny or stupid or something like that, you have to accept that and actually provide a good answer. And I think the debate and the discussions has been colored or colored by this sort of misunderstanding that the different perspectives, the different stakeholders, they think they understand the other your opponent, if I can call it that, but they may not have.
Yeah, well, that has been my experience, and that's a little bit why I'm doing this podcast, is to put the microphone in front of people from all different perspectives in the conversation and just let them talk for as long as they want until they feel understood. I mean, it's not only has my experience been that people misunderstand each other, but a lot of these people feel misunderstood. That was one of the big takeaways I had from doing some initial interviews for a research project, was everybody said, those people don't understand me and nobody's letting me talk to the end of my thought. I get cut off before I get to say what I'm thinking, and then it gets misrepresented. So one of the reasons I wanted to have you on early in this process is because I feel like you are not only knowledgeable, but fairly balanced. But do you feel like people often will perceive that you are kind of pro mining because of, I'm not sure why exactly,
Well, I guess, I mean, going back to 2014 again, I published this big number of a huge potential out there. And people saw money, kind of, because we translated those grades of copper into a monetary value.
Would you do that again if you were to publish it today?
Yeah, I think so. I think so. But I really also think that we should, and we have taken the initiative to some activity on it, is about having an activity on valuing the nature, not necessarily putting a number, a monetary value on it, because I'm not sure how to do that. But I'm by far an expert in valuing ecosystems, but I think we actually should do it. We should try to value ecosystems, put a value to it. There are probably experts in that may be listening here, but that I think would be interesting, because then you can start to actually compare it to other values, and based on that, perhaps make a better or more balanced decision.
Yeah, well, this is actually very specifically what I'm researching in my PhD on this subject. How do we get people to make decisions and even just have constructive discussions when we're talking about a conflict across value categories that don't align? How do you compare an economic value to an ecosystem value? And so I'm trying to ask everybody, I mean, you've sort of already answered this question, but I'm trying to ask it to everybody I speak with, is how do you approach this decision-making in situations of trade-offs, especially trade-offs with incommensurable or not comparable value categories?
Well, when it comes to deep sea mining, I've not been exposed to that decision. I've been more into trying to, understanding the geological potential better, trying to understanding how to develop technologies that could take different values into consideration, but we haven't really concluded on how to weight, for example, different values. So I would say, luckily, I guess I haven't been put into that situation where I would have to value it. We are in the process of trying to set up a framework, if I can use that word, to being able to value or to weight values when developing technology. Should you develop a mining technology or should you value, let's say, the monetary value more than the ecosystem value when developing a mining technology? And how should you weight them? We are very early in that process. But I think I need to come back to the understanding, because an understanding of the different values, and that can be achieved through dialogue. And again, it may be naive, but I think that we need to actually be able to talk better to each other, and it kind of goes without saying perhaps, but I see that we don't necessarily understand. I may not really understand the ecosystem value, and I need to understand that ecosystem value. And how can I achieve that understanding? By talking to you, by talking to others that understand it, and then we will kind of come up with together, hopefully, a common understanding on that will help us weigh these criteria. It may not be our task to actually weigh them, but we can actually, or we can at least perhaps inform the decision makers, and they will weigh them. So I'm not sure it's our role to do the weighing. I will produce my values, the values I work with. I will communicate them to you. You will communicate your values to me so that I can understand your values, you will understand mine, and we will achieve some common understanding, and we can then recommend something.
And also, I guess you're actively producing as much information that goes along with those values, so that not only can we have an abstract conversation about how our values compare to each other, but then we can dig down onto some of the details and look at the nuances of what we're talking about when it comes to the different value categories.
Yeah, and I think that how we have worked in the deep sea mining pilot and now also in the TripleDeep project is really through interdisciplinary cooperation, where we really put together interdisciplinary groups that are very different. They have very different mindsets. They have very different perspectives. And we kind of force ourselves and we forced them to discuss and compare and understand. And I think through that, and that's a long-term project. It's not really something you do over dinner. It's something you would do over many dinners, to put it like that, in really understanding each other and the luggage everyone brings in. That takes time.
Well, I feel like that's a good place to start wrapping up. But are there other topics, other kind of aspects that you'd like to cover before we come to the end?
I think we have covered a lot. I would stress that, and yeah, as you say, I may be perceived as someone who is pro deep sea mining, and I guess that goes back to my big number of what we may find. But I would stress that I'm not necessarily pro mining. I'm pro mining because we would need mining in the future. I'm not necessarily pro deep sea mining, but we need minerals. Our society needs minerals. I think we need to think holistically when it comes to minerals and metals. There are many sources. I'm not dragging space mining into this, but the space is there. I wouldn't claim we should do that for sure, but there are all sorts of legal issues when it comes to who owns the metals in space, so we will not take that discussion. But I think that it's fair to stress that deep sea mining may play a future role in, as I said before, meeting the future demand for minerals and metals. We have to be better at recycling, reuse. We have to develop onshore mining industry. You and I have to not necessarily buy a new phone every year. I'm not, but as a society, I think we buy and renew too much. We may actually drive our car until it really breaks down, instead of just replacing a 2-year-old car. Why do we have to do that? Why couldn't we design something so that it doesn't break? And I understand that something will break, or a thing will break eventually, but then it should be possible to fix it. And once it's fixed, once it's beyond repair, it should be possible to actually recycle and reuse the elements that are in that phone or car or whatever. We are not there yet. If you make a steel bar, it's extremely expensive, extremely difficult to actually extract the different components in that steel bar into the single elements so that you can make the same steel bar. So a steel bar that is recycled will probably end up being downgraded when it comes to value. So it will be downgraded into a less valuable product. So in order to make the steel bar that you wanted to recycle, you would have to mine as it is now. So we need to be better at recycling. We need to think broader. And as I said, deep sea mining may play a role. The demand will increase. I think all of us agree that the demand will increase. The disagreement is more on the speed, on how fast the demand increase will be. So all of us agree that our demand for minerals and metals will go up, and that demand increase will not be able to be met by recycling, for example. What is available for recycling today was what was put into production or was put into use, let's say 20, 30, 40 years ago. And what was the demand back then? Well, much lower than today. So if we were to recycle everything we put into use 40 years ago, that will not meet the demand today. And of course, your flat or your house, I don't know, you would like to have the copper wires for a couple of more years. You don't want to make it available for recycling. So, but of course, recycling should really play a role as well, and we need to be better at that. It's there are a lot of options out there, and there's a lot of dilemmas, ethical dilemmas that we need to face, that this industry needs to face and our societies need to face.
Well, you are an impressive example of how someone can hold multiple thoughts in the same head at the same time. It feels to me like is often the case in these discussions that people will choose one line of thinking and stick to it and amplify that. So it's nice to hear you kind of say that you're focused on one thing, but also see all of the other aspects are absolutely important and absolutely relevant in this discussion. Where can listeners follow you, keep up with your work, and where would you direct people to go to learn more about these topics?
Well, I work at NTNU. I'm a professor at NTNU. Google my name. You will find me on LinkedIn. To be honest, I'm not that active on LinkedIn. I'm not that good at spreading information there. But of course, you will find me on NTNU's web pages. I have a phone as well. It's getting old, but it's still working. Call me, send me an email. You will find the email address on NTNU web pages. So very interesting. If listeners are interested in something, I'm quite willing to discuss. Of course, the TripleDeep project is online. So if people would Google TripleDeep, they can also Google the deep sea mining pilot program. They can find information and my contact information related to that. So I'm online.
I'll put links to all of these things in the show notes.
Thank you.
Okay, Steinar Ellefmo, thanks for your time today.
Thank you. It's been a pleasure being here. Thank you.
I throw my arms up and to the side.